Have you ever pondered the possibility that space could undergo such profound bending that reality itself would be ruptured? Could the universe twist and fold in ways that our minds cannot fathom? What would our understanding of reality be like if space isn't as fixed as we believe it to be? These are the kinds of questions that challenge the boundaries of science and philosophy. What would happen if space itself were to unravel, shattering everything we know or perhaps tearing reality apart? Come along as we delve into these mind-bending concepts and find out. This is where the concept of spatial curvature comes into play. In simple terms, it refers to how space bends or curves depending on the amount of mass and energy present in the universe. When we think about the universe, it's easy to imagine it as vast and endless with no boundaries or edges. However, one of the most intriguing questions in cosmology is whether the universe has a specific shape and what that shape means for its future. Imagine a scenario where a heavy ball is placed on a trampoline. The surface of the trampoline will bend around the ball, and anything else on the trampoline will be pulled toward it. This bending or curvature also occurs on a smaller scale, but it is fundamental to our understanding of gravity and the large-scale structure of the universe. This is all according to Einstein's general theory of relativity. On a grander scale, spanning the entire cosmos, scientists have proposed three primary models to explain the nature of this curvature: flat, open, and closed. These models provide valuable insights into more than just geometry. They also provide light on the possible evolution and ultimate fate of the universe. In a flat universe, space is essentially uncurved. For example, consider a perfectly flat sheet of paper. Two straight parallel lines drawn on it will remain parallel regardless of how far you extend them. It implies that space is uniformly distributed and doesn't bend in any particular direction on the largest scales. In a flat universe, expansion would be an endless process, but gravity would eventually slow it down as it tries to pull everything back together. However, gravity wouldn't be powerful enough to stop expansion altogether. It would only slow it down. In the far future, everything could spread out so much that galaxies become isolated, stars burn out, and the universe becomes. In this model, space is curved like a saddle or a hyperbola, creating a frigid, dark place, sometimes called the Big Freeze. If you were to draw those same two parallel lines in an open universe, they would eventually diverge, moving farther and farther apart as you extended them. The universe would also keep expanding forever, but unlike in the flat model, it would accelerate. So in this scenario, the expansion would be faster. In the far future, as galaxies expand at ever-increasing speeds, some scientists have speculated that this could cause a big rip in space itself, tearing the fabric of space apart. In this scenario, the closed universe model comes into play. In this model, space is curved like the surface of a sphere. Imagine drawing two parallel lines on a globe. Eventually, they will meet. A closed universe suggests that space is finite but without boundaries, similar to how you can travel. The universe continues to expand indefinitely, never reaching an end. However, in a closed universe, gravity would eventually bring an end to expansion, causing everything to collapse in on itself. This would lead to the Big Crunch, in which the universe essentially rewinds, shrinking down to a hot, dense state similar to how it began with the Big Bang. Both models, open and closed, tell us something different about the universe's long-term future. But how can we tell which one is correct? An example of this is the correct cosmic microwave background, CMB. The CMB is a faint radiation that fills the universe and acts as a fossil record of the early universe. By studying small fluctuations in the CMB, scientists can learn about the distribution of matter and energy in the universe, which in turn gives clues about its shape. One of the most important things scientists look for in the CMB is the uniformity of its spread. If the cosmos is flat, then the cosmic microwave background, CMB, temperature fluctuations will look regular and evenly spaced. On the other hand, if the universe is open or closed, then the pattern of these fluctuations will be different due to the curvature of space. Based on what we know so far, it appears that the universe is almost flat. When scientists measure the CMB's curvature, the results reveal that any curvature is so tiny that it fits within the margin of error for our instruments. It's not an exact answer, but it does imply that the universe will keep expanding, albeit at a slowly decreasing pace, rather than ever ripping apart or collapsing in on itself. The universe may be slightly curved, though, in a way that we can't yet detect it. Even a small amount of curvature, if present, could alter the universe's final destiny. What's interesting is how these models relate to the idea of dark energy. This enigmatic force, which accounts for approximately 70% of the universe's total energy content, is driving the acceleration of the expansion of the cosmos. Its presence complicates our understanding of the universe's future, as it appears to be pulling space apart at an increasing rate. This could result in an open universe scenario, where the expansion continues indefinitely until a Big Bang occurs. On the other hand, if dark energy behaves differently it's difficult to predict what the future holds because we don't completely understand dark energy. However, what we do know is that space curvature plays a crucial role in shaping the destiny of the universe. Einstein's theory of general relativity introduced new ways of thinking about space, time, and reality. Before Einstein, people thought of space as Einstein's theory rewrote our understanding of gravity and the universe as a whole. At the heart of his theory are the Einstein field equations, which describe how space-time curves in response to mass and energy. The more massive an object, the more the curves, like a flexible fabric. Previously, we thought space was fixed and unchanging, but Einstein proved otherwise. As it expands, it distorts the space around it. For instance, the Earth's surface distorts space-time, which is why objects fall towards it due to gravity. However, the equations also foretell far stranger things, such as black holes, where space-time curves so sharply that not even light can escape. Gravitational waves, which are created when large objects collide, are ripples in this fabric of space-time. These ripples travel through space, stretching it. Gravitational waves squeeze matter as they pass through the cosmos, revealing previously unseen violent events like black hole collisions. Scientists didn't find a way to directly detect these waves until 2015, confirming Einstein's predictions. Gravitational waves are more than just a cool idea. They provide a new lens through which to study the cosmos. One of the first tests of general relativity occurred in 1919, shortly after Einstein published his theory, when a British astronomer, during a solar eclipse, Sir Arthur Eddington led an expedition to study the phenomenon. Since the sun's light was blocked, scientists could see the stars behind the eclipse. According to general relativity, the sun's gravity would bend the light from these stars, making them look slightly different than usual. Indeed, Eddington saw that the star's light was bent, proving that space-time is indeed warped by gravity. This was a historic proof of general relativity and catapulted Einstein to international fame. The effects of general relativity aren't merely theoretical. They permeate our everyday lives in subtle ways. One such example is the Global Positioning System, GPS, which uses signals transmitted by satellites in Earth's orbit to pinpoint our exact location. The catch is that, per general relativity, both the speed of the satellites and their distance from the Earth's gravitational pull make time seem to fly by. When we use GPS to get directions, we're actually benefiting from Einstein's theory of general relativity. Before general relativity, most scientists believed the universe to be moving at a constant, infinite speed, but now we know that satellites experience time slightly faster than us. Without accounting for this time dilation, GPS signals would become inaccurate, causing location errors of several kilometers every day. The Big Bang Theory, which postulates that the cosmos originated from a singular dense point and has been around since the Big Bang, was born in the 1920s when astronomer Edwin Hubble found that galaxies were receding from one another, providing direct proof that the universe is expanding. Initially, Einstein was troubled by this idea and even included a cosmological constant in his equations to make the universe appear static. The cosmos has been expanding since what Einstein later referred to as his greatest mistake, the addition of the cosmological constant. But this growth begs the question, what happens to the cosmos in the far future? Will it continue to expand indefinitely, or will it slow down and eventually collapse? The answers to these questions depend on a number of factors, including the quantity and composition of matter and energy in the universe, as well as the characteristics of a mysterious force known as dark energy. Currently, it appears to be driving the acceleration of the expansion of the universe. The evidence points to an infinite expansion of the universe, but scientists are still attempting to decipher the nature of dark energy. General relativity, as fascinating as it is, has its limitations. While it excels at describing massive objects like planets and stars and explaining concepts like the curvature of space-time, it becomes a disaster when applied to microscopic scales, such as within a black hole or the early stages of the Big Bang. The equations become incoherent. This is where quantum mechanics comes into play. It is this theory that explains the behavior of particles on the tiniest scales, and it doesn't fit well with general relativity. In fact, the two theories appear to depict two completely separate realities. How to reconcile these two theories is one of the greatest mysteries in physics. Another peculiar prediction of general relativity is that of quantum mechanics. At the heart of every black hole lies a singularity, where the curvature of space-time becomes infinitesimally small and the conventional laws of physics cease to apply. At this point, the force of gravity is so great that space-time itself collapses, and what happens after this point is a mystery. Singularities indicate that our knowledge of the cosmos is lacking. There are locations where the reality described by general relativity appears to. It's important to note that general relativity alters our everyday perception of time. Previously, we believed that the passage of time was uniform and unchanging across all locations and masses. However, as we've seen in experiments, the theory now reveals that this is not the case. Rather, time dilates due to gravitational pull and speeds up as one moves away from massive objects like stars and planets. By way of illustration, before Einstein, people believed that space and time were independent entities. That is, that space was the location of objects and time the force that caused them to move. However, general relativity demonstrates that space and time are in fact interdependent. For instance, when large objects distort space, they also distort time. This explains why time seems to slow down in the vicinity of a black hole or other strong gravitational field. It's also black holes, infinite curvature, and the collapse of reality are among the most enigmatic and extreme objects in the universe. They test our knowledge of physics and pose a challenge to the very concept of reality. When you think of a black hole, your mental image is likely of a dark, bottomless pit. However, astronauts on the International Space Station appear to experience time flowing differently due to their rapid acceleration and increased distance from Earth's gravity. That singularity engulfs all in its path, leaving no way out. While this is mostly accurate, the truth about black holes is far stranger than you might think. These celestial objects are born when enormous stars collapse, concentrating all their mass into a tiny point. The result is a gravitational force so powerful that not even light can escape beyond a certain point. However, black holes are more than just cosmic vacuum cleaners. There are also locations where at the event horizon, the edge of a black hole, nothing can escape its gravitational pull. Once something crosses this boundary, there is no turning back. This idea is related to the Schwarz-Ch radius, named after the German physicist Karl Schwarz, who originally proposed it. When we understand black holes, we learn about the fundamental breakdown of the laws of physics as we know them, which goes beyond studying gravity to explore the boundaries of space, time, and reality. The distance from the center of a black hole to the event horizon, known as the Schwarzschild radius, is directly related to the mass of the black hole. For instance, if Earth were compressed into a black hole, its Schwarzschild radius would be approximately equal to that of a marble. The event horizon is not a physical surface. Rather, it is more akin to a wall. Beyond this point, space and time become distorted due to the black hole. It's strange that despite their centrality to our understanding of black holes and the universe as a whole, we don't fully understand singularities. At the center of every black hole, there lies a singularity where matter is crushed down to infinite density. At this point, all paths lead inward toward the center, where something even more bizarre awaits, the singularity. Here, physics ceases to function. It's difficult to comprehend the concept of a black hole or any object that collapses into a singularity because it doesn't conform to our normal experience. Normally, when something is compressed, it still occupies space. However, at a singularity, space disappears entirely. The gravitational pull is so great that space-time curves infinitely and nothing, not even light, can escape. The laws of physics, as we know them, collapse at a singularity. General relativity, which explains gravity and the behavior of massive objects, predicts the existence of singularities but cannot explain what happens inside them. This is due to the fact that, when applied to points of infinite density, the equations of general relativity start to give nonsensical answers, suggesting that our present-day physical theories are insufficient and fail to adequately explain what occurs in. In these extreme settings, the search for a theory of quantum gravity becomes relevant. Currently, there are two main frameworks for making sense of the cosmos: general relativity, which describes large-scale objects like galaxies and stars, and quantum mechanics, which describes the behavior of subatomic particles. However, these two theories are at odds with each other, and the conflict between them becomes particularly apparent at singularities. At a singularity, matter can become infinitely dense, but quantum mechanics predicts that there must be a limit to how much matter can be compressed. To overcome this paradox, physicists are trying to build a theory of quantum gravity that integrates quantum mechanics and general relativity. This theory would shed light on what happens at singularities, both inside black holes and at the Big Bang itself. Regrettably, a comprehensive theory of quantum gravity remains elusive, despite the ongoing investigation of theories such as loop quantum gravity and string theory. In the realm of singularities, there's an intriguing concept known as the cosmic censorship hypothesis, put forth by physicist Roger Penrose in the 1960s. This theory proposes that, in all cases, an event horizon, the boundary surrounding a black hole, keeps all singularities hidden from the rest of the universe, from which nothing can ever escape. In a nutshell, the cosmic censorship hypothesis states that singularities cannot be naked or exposed to the outside world because they are always surrounded by an event horizon. This explains, in theory, why black holes contain singularities and prevents them from causing a physical breakdown that would otherwise disrupt the cosmos. On the other hand, there are theoretical situations in which this theory could be incorrect. Hidden behind event horizons, these so-called naked singularities would be exposed to the universe, posing a host of problems for our physics understanding. If they do exist, they could be locations where the usual laws of cause and effect collapse, leading to unpredictable and potentially harmful consequences. At present, there is no direct evidence for naked singularities, and most black holes appear to adhere to the guidelines outlined by the cosmic censorship hypothesis. However, singularities also play an important part of our knowledge of the early cosmos. Just as every black hole has a singularity at its core, so too did the universe have one at the Big Bang. According to the Big Bang theory, the cosmos expanded from a very hot and dense state at the beginning of time. But before this expansion started, the entire cosmos was compressed into a point of infinite density, a singularity. Similar to black hole singularities, where the laws of physics fail at extremely high densities and temperatures. Similarly, our current understanding of the Big Bang singularity necessitates a theory of quantum gravity. This theory could shed light on the universe's emergence from this initial state of infinite density and provide a more precise description of the events that transpired during the early moments of the cosmos. After the Big Bang, there are points in space-time called singularities. At these points, space-time becomes so distorted that our conventional understanding of it breaks down. For instance, as you get closer to a singularity, time stops moving because the gravitational pull is so strong. Beyond the point of recognition, space-time becomes entangled in ways that are hard to fathom. As the boundary between the two gets more porous, the collapse of space-time at singularities casts doubt on the stability and fundamentality of these concepts. In our daily lives, we perceive space and time as immutable dimensions, but singularities reveal that, in certain extreme cases, these dimensions can collapse and fall apart. This has prompted some physicists to propose that space and time are actually emergent properties, originating from deeper, more fundamental processes. The information paradox, when an object, a star, a planet, or even a simple particle, falls into a black hole, it passes beyond the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. Once it crosses the event horizon, it is lost to the outside universe forever. This theory challenges our current understanding of space and time. Conundrum: if information falls into a black hole, does it get destroyed, or is there a way for it to be preserved? This is a perplexing question because, according to quantum mechanics, information must always be conserved. This implies that the total amount of information in the universe should stay constant over time. Even if, for instance, you burn a book, the information inside will not be lost, but may be transformed in a heat. The information paradox at its core is the idea that information could be destroyed in a black hole, which conflicts with quantum mechanics, which insists that information must be preserved, despite the fact that the fundamental information about the atoms and molecules that made up the book still exists, even if it's scattered. This is in contrast with black holes, which seem to defy this rule. Physicist Stephen Hawking, who made significant contributions to our understanding of black holes and the information paradox in 1974, made a groundbreaking discovery: black holes aren't entirely black. This prediction sparked decades of debate and challenged our understanding of quantum mechanics and general relativity, the theories that describe the behavior of massive objects like black holes. Hawking radiation is a faint form of radiation emitted by black holes. It is believed to originate from quantum effects close to the event horizon. When two particles are created just outside the event horizon, one of them falls into the black hole and the other escapes into space. As a result, the black hole loses mass and shrinks. If Hawking's theory is true, then black holes will eventually evaporate, releasing all of their mass as radiation. This process brings up an intriguing. The black hole information paradox began with a heated debate among physicists over whether or not black holes violate the rules of quantum mechanics. At first glance, it may appear that Hawking radiation could carry the information about everything that fell into a black hole, but this raises the question of what happens to the information once the black hole evaporates. Information regarding the objects that were swallowed by the black hole. But there's a catch. Hawking radiation is entirely random. It doesn't appear to contain any data regarding the matter that was originally swallowed by the black hole. If the information is encoded in the random radiation that the black hole releases as it evaporates, then that data is effectively lost, irretrievably scrambled. This concept didn't sit well with many physicists who were hesitant to embrace the idea that information. Some physicists have put out the theory that the data might not be completely erased, but rather encoded in a highly garbled form in the Hawking radiation. This would be analogous to how data in a burned book isn't completely erased, but rather scattered and difficult to reconstruct. The problem with this theory is that Hawking radiation is so random that it's not clear how the data could be recovered, even in the event that it miraculously resurfaces. The information paradox remains unsolved in this case, because, according to the principle, if data is so badly corrupted that it can never be recovered, does that really constitute information conservation? A different way of looking at things is through the concept of complement mighty, which states that data could be either destroyed or preserved. It all depends on your vantage point from outside the black hole. Data isn't really lost, but encoded in a complicated way close to the event horizon. From the viewpoint of someone falling into the black hole, though, it appears as though all information vanishes into the singularity at its center. This contradictory view allows for the coexistence of information conservation and Hawking's theory of black hole evaporation. though it does leave many unanswered questions. A new theory that could solve this problem, based on the holographic principle, has emerged in recent years. It originates from, like a hologram, which encodes a three-dimensional image on a two-dimensional surface. String theory proposes that all the information about what goes into a black hole might be stored on its surface, not inside the black hole itself. If this holographic principle holds, then all the information about what goes into a black hole could be encoded on its event horizon, and this information could be preserved even when the black hole evaporates, solving the mystery. The holographic principle has been the subject of much speculation as a potential solution to the information paradox. However, unlike many other ideas in theoretical physics, it guarantees that no data is ever really lost. Rather, it is stored in a manner that defies conventional wisdom. By studying black hole entropy, a measure of a system's disorder, physicists made a significant advance in 2019. It may sound strange to think of black holes as having a temperature, but the idea that black holes can evaporate brings us to another mind-bending concept: black hole thermodynamics. This research has revived hope that the information paradox might one day be solved, but it's far from a definitive answer. I've discovered that certain quantum corrections to Hawking's original calculations might allow information to escape from a black hole in a more organized way than previously thought. Theoretically, smaller black holes could theoretically become extremely hot just before they vanish entirely. Hawking's theory states that black holes get hotter as they shrink in size, while massive black holes at the centers of galaxies are extremely cold. Black holes also have entropy, which is a measure of the amount of disorder or randomness in a system. Here's where things get weird. A black hole's entropy isn't proportional to its volume, as one would expect, but to the surface area of. Its event horizon has prompted some scientists to believe that black holes store all the data about their contents in an encoded form on their surface, similar to a hologram. If this theory is correct, it could lead to a more profound link between quantum mechanics, gravity, and thermodynamics. Black holes aren't theoretical, though. They exist and can be detected in various ways. One of the most exciting ways we've seen black holes lately is through gravitational waves, which are ripples in space-time caused by the acceleration of massive objects like black holes colliding, are a game-changer for astronomy. Until 2015, scientists could only observe black holes indirectly by watching their effects on Earth's magnetic field. However, with the discovery of gravitational waves, a prediction of Einstein's theory of general relativity was confirmed, and the field was able to move forward with confidence. Black holes have long been a mystery, but today we can listen in on their collisions and mergers to learn more about their masses, spins, and interactions with one another. By detecting gravitational waves, we gain direct evidence of black holes and new insights into the nature of space-time. Gravitational waves also allow us to test the limits of general relativity. Einstein's theory of relativity has been very successful in describing the cosmos on large scales, but it hasn't been tested in the extreme environments close to black holes. Black holes pose a number of challenges to our current understanding of the universe, including: what happens inside a singularity? Is information really destroyed? And how does gravity in the quantum world fit in? In physics, black holes may hold the answer to some of the most fundamental questions about the nature of reality. At the same time, as we learn more about them, through gravitational wave detection, black hole thermodynamics research, and the never-ending search for a solution to the information paradox, we can expand our understanding of these fascinating phenomena. Inflation is a well-established theory that opens the door to some mind-bending ideas, like the possibility of a multiverse. The fast expansion of space during inflation answers many questions about the early universe, but also raises new ones about the nature of existence. In the first moments after the Big Bang, the universe was in a hot, dense state, and scientists are still captivated by holes and its challenges to our understanding of the cosmos. Imagine a proton suddenly expanding to the size of a galaxy. That's the kind of mind-blowing growth that inflation represents in the first trillionth of a second. This expansion occurred at a rate much faster than the speed of light, causing space to grow by an unfathomable amount in an extremely short time. This is the theory of cosmic inflation, which proposes that the universe expanded exponentially within that first trillionth of a second. It, first proposed by physicist Alan Guth in 1980, resolves numerous long-standing cosmic mysteries. One of its primary issues is the so-called horizon problem, which, in layman's terms, is the observation that various regions of the universe seem to have almost identical structure and temperature, despite being too distant to have ever influenced each other without inflation. It's difficult to explain how these regions could have grown so similar, because there wasn't enough time for light or information to travel between them before they expanded to their current size. Inflation, on the other hand, suggests that the universe was small enough before the rapid expansion for all regions to be in close contact. As space expanded during inflation, these regions were stretched far apart, but they kept the similarities that formed when they were much closer together. This explains why the universe appears uniform on large scales, even though there was no information or light traveling between them. The universe is smooth and homogeneous on large scales because inflation stretches out any irregularities. This explains why, even though the universe contains vast structures like galaxies and clusters of galaxies, it appears relatively uniform when viewed from a distance, even though its parts are now separated by billions of light years. Without inflation, the universe could be lumpy and uneven with areas of wildly different densities. The role of inflation extends far beyond simply smoothing out the early universe. It is crucial in the formation of galaxies and other structures that we observe today. During the inflationary period, small quantum fluctuations, essentially random microscopic variations in energy, were stretched to enormous sizes. These fluctuations, which began as tiny blips at the quantum level but were blown up to cosmic scales by the rapid expansion of space over time, serve as the basis for the formation of galaxies, stars, and other structures found in the universe. Despite its tremendous power and speed, cosmic inflation didn't endure long. It ended after a minuscule fraction of a second. However, what followed was pivotal in forming the universe as we know it. With inflation ending, the energy that had driven the fast expansion was released, triggering a period called reheating. During this reheating, the universe became filled with particles and radiation, establishing the start of the hot, dense state that is associated with the early universe. Additionally, reheating is when the standard model of particle physics describes the development of the particles and forces that comprise our universe. During this period, the universe went from an unfamiliar inflationary state to one that was more familiar, filled with the particles that would later form atoms, stars, and galaxies. Without reheating, the universe would have stayed a cold, empty expanse of space. However, this phase began the processes that would eventually lead to the formation of everything we observe today, and inflation ended with our. One of the most fascinating ideas to emerge from inflationary theory is the concept of an inflationary multiverse. This theory proposes that different regions of space could undergo inflation at different times, resulting in separate universes with their own physical laws and properties. The observable universe is a potential location where inflation ended, but other regions could still be experiencing it. This idea is still speculative, but it's intriguing because it expands the implications of inflation far beyond our observable universe. The concept of the inflationary universe offers a fascinating alternative, where each pocket universe could be drastically different from the others. Some could have different laws of physics, while others could have different fundamental constants like the charge of the electron. This theory proposes that new universes are constantly being created in different parts of the multiverse as a result of eternal inflation. This idea challenges our understanding of reality and suggests that our universe is just one small part of a much larger system of interconnected universes. The holographic principle suggests that our universe is a projection of this system. It's a challenging idea to think that the three-dimensional universe might actually be a projection of information stored on a two-dimensional surface. This goes against our natural understanding of space and reality. To understand more about this, we need to look at the holographic hypothesis and how it relates to black holes, entropy, and cosmology. Physicist Gerard II initially proposed the holographic hypothesis. The holographic principle, proposed by Leonard Susskind in the 1990s, is an audacious effort to resolve physics mysteries with a focus on black holes. It proposes that, just like a hologram, where a two-dimensional image can give the impression of a three-dimensional object, the whole cosmos that we perceive in 3 dimensions may in fact be the product of data stored on a distant, two-dimensional surface, dimensional boundary, which could be located at the very edge of the universe. This theory poses a serious challenge to our fundamental assumptions about the nature of reality. Typically, we imagine the world as a three-dimensional space where objects have dimensions of length, width, and depth. However, if the holographic principle is true, then these dimensions could simply be a projection from a lower dimensional space. This is a very different way of looking at the universe, but it does have some conceptual backing. This principle is derived from the study of black holes, which have long fascinated physicists due to the extreme conditions they induce in the laws of physics. At the heart of a black hole, there's a singularity where matter is compressed to an infinite density and the laws of physics collapse. The area around the black hole is called the event horizon, and beyond this point, not even light can escape the black hole's gravitational pull. In the 1970s, physicist Jacob Bekenstein made a groundbreaking discovery. The entropy of a black hole isn't directly proportional to its volume, contrary to popular belief, but rather to the area of its event horizon. Entropy, which is a measure of disorder or randomness in a system, typically scales with volume, but in the case of black holes, it scales with the area of the event horizon. This finding was later corroborated by Stephen Hawking's discovery, which suggested that all the information about what has fallen into the black hole is encoded on its surface rather than inside its volume. Hawking's calculations revealed that a black hole's entropy decreases in proportion to the surface area of its event horizon, rather than its volume, as it loses mass and radiates energy. This intriguing correlation between the two led to the hypothesis that all the information about what goes into a black hole is encoded on its surface. If this is indeed the case, then the implications of this finding are profound. At its core, the holographic principle proposes that the entire cosmos, like a hologram, may contain all of the information contained in our three-dimensional universe encoded on a two-dimensional boundary, much like a cosmic hologram. To better understand this, one could picture the universe as a massive three-dimensional projection, similar to how a hologram produces an image on a two-dimensional surface. Space and time may be seen as emergent properties, resulting from more fundamental processes occurring on this faraway 2D surface. This surface could be the boundary of the universe, something beyond the edge of our observable universe that may be connected to its expansion. The idea that the universe is projected from this surface is both mind-boggling and deeply implicative for cosmology, potentially resolving the black hole information paradox, which stems from the seeming conflict between quantum mechanics and general relativity. This idea has gained traction in theoretical physics and has the potential to revolutionize our understanding of reality. Rather than seeing physical objects and events as occurring in our three-dimensional space, we may be witnessing processes that take place far beyond our field of vision. Since information about a system can never be destroyed, this idea could preserve the integrity of quantum mechanics while still allowing black holes to behave as predicted by general relativity. Specifically, if the holographic principle is correct, then information is not lost when it falls into a black hole, but rather stored on its surface, similar to how a hologram stores information about a 3D image on a 2D surface. A branch of physics called string theory that aims to bring together quantum mechanics and general relativity. In this theory, the holographic principle is crucial to comprehending how gravity operates. However, the implications of this principle extend far beyond. Black holes. If the entire universe is holographic, then all information about the universe, including the positions and properties of every particle and field, could be encoded on a distant boundary. This leads to the even more radical question: is the universe an illusion? Could it be that what we perceive as solid three-dimensional reality is actually a projection from something deeper and more fundamental? Some versions of string theory propose that our universe exists on a 3D brain, which is short for membrane, floating in a higher dimensional space with the information about our universe encoded on a 2D boundary. If space and time are emergent properties, as the holographic principle suggests, then the very fabric of reality itself could be a perception. The very nature of reality itself is up for debate. What we perceive as happening in the cosmos may actually be the product of data processing taking place at the very periphery of our galaxy. Another intriguing and mystifying concept in contemporary cosmology is dark energy, which appears to be speeding up the expansion of the universe and contradicting our expectations regarding its behavior. The discovery of dark energy has sparked new theories about the end of the universe, including the terrifying prospect of a Big Bang. The story of dark energy starts with the idea that the universe is expanding, first proposed by astronomer Edwin Hubble in the 1920s. Hubble's observations revealed that distant galaxies were moving away from the galactic center, which raised profound questions about the ultimate fate of the universe. However, little is actually known about what dark energy is. Based on our understanding, the universe has been expanding for a long time. However, scientists used to think that gravity would slow down this expansion, or perhaps even stop it altogether, which would make the universe static or even cause it to collapse in on itself. That all changed in the late 1990s when two separate teams of astronomers made the shocking discovery that the expansion was actually speeding up. Scientists discovered that the expansion of the universe had been increasing for billions of years by studying the light from faraway supernovae. This discovery completely turned cosmology on its head because it meant that there had to be a force driving this acceleration, something that could counteract the pull of gravity. This mysterious force became known as dark energy. It is believed to account for approximately 70% of the universe's total energy content. It's an incredibly. Dark energy is a mysterious and powerful force that has scientists reevaluating their theories about the cosmos. Previously, scientists had assumed that the universe would either expand indefinitely or contract, but now we don't know what it is or where it originates. Instead of pulling objects closer together, dark energy appears to have the opposite effect, pushing them farther apart. The cosmos should either expand steadily or eventually collapse in on itself as a result of gravity, but dark energy has changed all that. Now, it appears the universe will keep expanding at an ever-increasing rate, which has huge consequences for the future of the universe. What's most astonishing about dark energy is how little we know about it. We can measure its effects on expansion, but we don't know what it is or how it works. Some scientists have even proposed that dark energy could be a consequence of. According to this theory, space itself expands, which in turn causes more dark energy to be created, and the expansion continues in a feedback loop. On the other hand, some have suggested that dark energy could be connected to the cosmological constant, a concept that Einstein included in his general relativity equations to describe a force that counteracts gravity and prevents the universe from collapsing. After Hubble's discovery of the expanding universe, Einstein referred to the cosmological constant as his biggest mistake, but it appears that this idea may have been more in line with the. There are new theories about the universe's evolution that have been sparked by the discovery of dark energy. Some propose that dark energy could eventually fade away, while others suggest that it could become even more dominant in the future with catastrophic consequences. Einstein himself acknowledged the possibility that dark energy is related to a new field or particle that has not yet been discovered. Dark energy is speeding up the expansion of the universe at an ever-increasing rate. In this scenario, known as the Big Rip, the expansion is so powerful that it could tear apart galaxies, stars, planets, and even atoms. To understand the Big Rip, it's helpful to think about how gravity and dark energy interact. Currently, galaxies are held together by gravity, which counteracts the expansion of the universe on smaller scales. The reason galaxies and galaxy clusters don't expand at the same rate as the universe is because gravity is strong enough to keep them bound together. However, in the Big Rip scenario, everything would be ripped apart by the expanding space around them if dark energy keeps speeding up the expansion of the universe. Stars, planets, and even tightly bound systems like galaxies would be at risk. At the most microscopic level, galaxies, star systems, planets, and eventually even atoms and subatomic particles could be ripped apart by the cosmic vacuum that would result from dark energy's dominance. The prospect of a great rip is terrifying, but we must not lose sight of the fact that this is only one of many possible outcomes. The fate of our universe ultimately rests on dark energy's characteristics. Our understanding of dark energy is limited and its long-term behavior is uncertain. If it remains constant, as it seems to be at the moment, the universe will expand indefinitely, but at a slower rate than the Big Bang scenario predicts. In this scenario, galaxies would drift apart, and the universe would eventually reach a maximum state of expansion after trillions of years of star burnout and galaxy extinction. Since there is no longer any energy to power stars or other cosmic processes, there are alternative, more theoretical theories regarding how dark energy may influence the Big Bang. One such theory is that dark energy could eventually become weaker or even reverse, causing the expansion of the universe to slow down or come to a halt. If this were to happen, gravity would once again pull everything back together in a big crunch, and the universe would collapse back into its original hot, dense state. Some cosmological theories postulate that our universe may be one of many interconnected multiverses, each with its own unique set of physical laws and properties. In this scenario, dark energy may play a role in the birth of new universes, with various parts of space expanding at different rates, thus creating the possibility of periodic expansion and contraction of the universe, punctuated by Big Bangs. Regardless of the many unanswered questions about dark energy and its role in shaping the fate of the universe, one thing is certain. It plays a crucial role in determining how the universe evolves in the future. Whether this leads to a Big Bang, a big freeze, or some other outcome, the discovery of dark energy has intriguing questions about reality and the possibility of other universes beyond our own. Time, which we normally perceive as flowing uniformly for all, can actually be stretched, slowed down, or even nearly stopped depending on factors like gravity and velocity. However, when space bends, or when objects move at incredible speeds, time behaves differently. What does this mean for our understanding of the universe and our place in it? Let's take a look at how space bending warps the flow of time. And Einstein's theory of general relativity predicts that massive objects, such as planets and stars, bend the fabric of space-time. This curvature affects the flow of time. The stronger the gravitational pull, the more space-time is warped, and the slower time moves in that region compared to a place without a strong gravitational field. This phenomenon manifests itself in a variety of contexts, from Earth to the extreme environments of black holes. To help illustrate this point, let's compare the speeds of clocks on Earth and those in orbit. Here on Earth, we're relatively close to the center of gravity, so the gravitational field is strong. However, in orbit, where gravity is weaker, clocks aboard satellites tick slightly faster than those on the ground. This isn't just an abstract idea. It's a well-documented effect, for example, with the Global Positioning System, GPS, which we use on a daily basis. Depend on for navigation accounts for gravitational time dilation. The GPS satellites orbit around 20,000 kilometers above Earth, with a weaker gravitational pull causes time to run slightly faster. Without this correction, the GPS systems would be off by several kilometers per day, rendering them practically useless for accurate navigation. The idea that gravity can distort time becomes even more extreme when considering extremely massive objects, such as black holes, in close proximity to one another. As one gets closer to a black hole, the gravitational pull becomes so strong that time dilation becomes so extreme that it appears to almost stop for someone far away. An object falling toward the event horizon would appear to slow down and never quite cross it from the object's perspective. From outside the event horizon, however, time appears to pass normally. Once the object crossed the event horizon, however, the concept of relativistic time dilation, which originates from Einstein's earlier theory of special relativity, concerns the possibility that time could theoretically freeze at the boundary of a black hole. This extreme dilation of time near black holes is one of the most peculiar predictions of general relativity and has sparked widespread fascination in discussions regarding space and time. Let's pretend for a moment that astronauts are traveling to a faraway star at a speed close to the speed of light. Because of the laws of special relativity, time slows down for objects as they approach the speed of light. This effect becomes more noticeable the faster something moves. Consequently, a spaceship clock would tick much more slowly than an Earth clock. What may seem like a short journey for astronauts could actually be decades, or even centuries for those on Earth stuck behind because of relativistic time dilation. The classic thought experiment known as the twin paradox shows this in action. While one twin stays on Earth, the other travels into space at nearly light speed. When the spacefaring twin returns to Earth, they discover that this paradox illustrates how relative motion determines the passage of time and has been proven experimentally. One of the most well-known examples of time dilation is the 1971 experiment, in which scientists strapped extremely accurate atomic clocks to airplanes and flew them around the globe, comparing the time they recorded with identical clocks on the ground. The clocks on the airplanes were traveling at high speeds relative to the clocks on Earth, demonstrated a small but discernible slowing of time. This experiment proved relativistic time dilation and proved that even at the speeds we can reach with airplanes, the effects of time dilation are real. Similarly, satellites in orbit undergo both gravitational and relativistic time dilation. GPS and other systems based on satellites account for both types of dilation to ensure their accuracy, even though there is a small. One of the most fascinating examples of time dilation in the universe comes from faraway galaxies and the light they emit. This is called cosmological time dilation, and it happens when space itself expands the wavelengths of light from objects billions of light years away. Time dilation isn't just something that people wonder about in theoretical physics labs and science fiction stories. It's also an essential part of cosmology. The redshift is caused by the stretching of galaxies, which alters the color of the light and also makes it appear as though time has slowed down. This effect is especially noticeable when we observe distant supernovae, which are the explosive deaths of stars. Typically, the light from these supernovae follows a predictable pattern, but when we observe them in distant galaxies, we notice that their light curves. At the most fundamental level, at the level of atoms and particles, there exists a domain where our everyday perception of space and time is impacted by quantum fluctuations. This manifests as a lengthened rise and fall in the brightness of distant objects as time passes. This effect is a direct outcome of cosmological time dilation, which occurs because the universe has expanded since these objects' light was emitted. Space and time do not exist in a continuous and smooth form as we perceive them. Instead, they are composed of a chaotic, ever-changing structure called space-time foam. This idea was proposed by physicist John Wheeler in the 1950s, and it proposes that at very small scales, particularly the Planck scale, space-time is a frothy, seething mess of quantum fluctuations. These fluctuations occur so quickly and at such small scales that they imply that space-time is continuously bubbling. In order to comprehend space-time foam, it is necessary to understand the significance of the Planck scale. This scale, which measures approximately 16 times 10 to the power of 35 meters, is the smallest meaningful unit of distance below which our familiar notions of space and time collapse under the influence of quantum uncertainty. At this point, quantum mechanics governs, and our familiar ideas of geometry, distance, and time become nebulous. The Planck scale is where the smooth continuity of space-time predicted by general relativity gives way to a structure resembling a foam, wherein tiny bubbles of space-time emerge and vanish at regular intervals. These fluctuations in quantum mechanics are caused by the uncertainty principle, a fundamental tenet of the field, which states that we can never know two properties of a system. In this instance, position and momentum, exactly at the same time. Space-time destabilizes itself at the most fundamental level due to the formation of tiny, ephemeral structures like microscopic black holes and wormholes. These fluctuations are too small to be directly observed, but their existence is predicted by quantum mechanics. At extremely small scales, space-time is no longer a static backdrop for events. It becomes a dynamic, shifting entity where space and time fluctuate unpredictable. Quantum mechanics on the Planck scale, the energy levels of these fluctuations can be so high that they can momentarily form tiny black holes, which exist for an instant before vanishing. These tiny black holes are completely unlike the massive stable black holes we see in space. They are ephemeral events that exist solely as a result of the extreme energy levels found at the quantum scale. Similarly, these fluctuations can also give birth to microscopic wormholes, which are tiny tunnels through space-time that could link various parts of the cosmos, even if only for a nanosecond. The concept that space-time could be brimming with these minute, transient structures is absolutely mind-boggling. It implies that, deep down, space-time isn't a smooth continuum but a frothy, turbulent sea of quantum activity. These fluctuations blur the boundary between space and time, making it impossible to measure distances or durations with absolute precision. At these scales, becoming less separate and more entangled. One of the most significant implications of space-time foam is that it questions our notion of reality. If space-time is inherently unstable, then our universe rests on an equally unstable framework. This goes against the grain of classical physics, which holds that space and time provide a static, stable background against which events take place. Space-time foam is also important in the quest for a theory of quantum gravity. This theory seeks to combine general relativity, which explains the behavior of massive objects on large scales, with quantum mechanics, which governs the behavior of particles and forces on small scales. Both theories have been remarkably successful in their own fields. Contrary to popular belief, quantum mechanics describes a world of probabilities, uncertainty, and discrete quantities, while general relativity views space-time as a smooth continuum that can be bent and curved by the presence of mass and energy. Space-time foam offers a glimpse into the potential convergence of these two theories at the Planck scale, where space-time fluctuations dominate and the effects of both gravity and quantum mechanics become equally important. The development of a theory of quantum gravity hinges on how it acts at this scale. Theoretically, space-time foam could stand in for space-time's quantum behavior, illuminating the quantum nature of gravity and providing insights into how to bridge the gap between the two theories. A significant hurdle in this endeavor is the fundamental dissimilarity between the mathematical frameworks of general relativity and quantum mechanics, the former dealing with discrete quantized quantities and the latter describing smooth. One of the leading contenders for a theory of quantum gravity, string theory, provides a framework for understanding space-time foam. This theory posits that space and time may not be continuous at the smallest scales, but rather comprise discrete, fluctuating structures. If this is so, then space and time could be quantized, existing in discrete units similar to energy in quantum mechanics. Space-time is believed to originate from the interactions of these strings with space-time foam, which represents the fluctuating behavior of space-time in this higher dimensional framework. Loop quantum gravity, another method for understanding quantum gravity, also sheds light on space-time foam. Rather than point-like particles, the particles and forces we see in the universe at the Planck scale are actually tiny vibrating strings. Both theories propose different explanations for the existence of space-time foam, but none has been proven conclusively. One theory proposes that space-time is made up of discrete quantum field loops that form a network and give rise to its fabric at the Planck scale. Another theory, loop quantum gravity, posits that space-time is not a continuous fabric, but rather a network of interconnected loops that are constantly changing and evolving. For the time being, our technology isn't advanced enough to directly observe space-time foam. but there is hope that its effects on high-energy cosmic rays or the behavior of light traveling vast cosmic distances could provide indirect evidence. For instance, space-time foam could cause tiny distortions in the paths of light from faraway galaxies, which would be detectable in the cosmic microwave background radiation. Cosmic strings have long been postulated as remnants from the early universe, possibly emerging from phase transitions that happened soon after the Big Bang. If they exist, their enormous gravitational effects could teach us new things about the nature of space-time and how it came to be. However, we have not yet been able to directly detect these hypothetical, one-dimensional objects, which could span enormous distances in space and possess tremendous mass and energy. Cosmic microwave background radiation, gravitational waves, and other astrophysical phenomena to support the hypothesis of cosmic strings, which were initially proposed in the 1970s by physicists seeking to explain the quick expansion and subsequent cooling of the universe following the Big Bang. Since then, the search for these strings has persisted, with scientists investigating various large-scale structures in the cosmos and even basic physics. Cosmic strings are one example of a topological defect in space-time that may have formed during phase transitions analogous to those that occur when water changes from a liquid to a gas. These strings are believed to be extraordinarily thin, maybe as narrow as a proton, but exceedingly long, potentially spanning galaxies or the entire universe. Despite their incredibly thinness, cosmic strings would contain an enormous amount of mass and energy, rendering them extraordinarily powerful gravitational forces. In contrast to particles, which are two-dimensional points, and membranes, which are one-dimensional surfaces, cosmic strings are one-dimensional filaments that stretch through space like endless wires. The tremendous energy density of cosmic strings is believed to originate from the tension along their length, similar to how a taut rubber band contains potential energy. The string's tension is so high that even a tiny portion of it could halve. One of the most remarkable aspects of cosmic strings is their capacity to bend space-time. According to Einstein's theory of general relativity, massive objects, including cosmic strings, cause space-time to curve. However, cosmic strings are narrower than planets and stars, so they bend space-time in a very different way. If such strings existed, their gravitational effects would be substantial. The most prominent of these observable effects could be gravitational lensing, which happens when light from faraway objects, like galaxies or stars, passes near a massive object on its way to Earth. This distortion, known as a conical distortion in space-time, is often compared to a deficit angle, in which space around a string is slightly compressed, giving it a wedge-like appearance. If a cosmic string were to pass in front of a distant galaxy, it would cause gravitational lensing, which distorts or duplicates distant objects. Another type of lensing that cosmic strings can create is unusual arcs of light or multiple identical images of the same galaxy. This effect could be used to detect cosmic strings because their gravitational effects on light are easily identifiable. Gravitational waves are ripples in space-time that result from the acceleration of massive objects. In 2015, scientists made the first detection of gravitational waves when two black holes merged. These waves could be created in a number of ways, such as a collision between cosmic strings or the collapse of a single string that formed a loop. Either way, they would disturb space-time and send ripples through space-time, potentially causing catastrophic events. Possibly picked up by gravitational wave observatories like the LIGO Laser Interferometer or future gravitational wave detectors. Cosmic strings were believed to have formed during phase transitions in the early universe, when the cosmos cooled and expanded in the immediate aftermath of the Big Bang. During these transitions, various physical forces and fields froze out, much like water turns into ice. At the same time, the symmetry of the cosmos broke in. Strings of space-time could have been stretched across the expanding universe, like ice cracks as they freeze. This stretching could have shaped the structure of a universe on a large scale. Strings of space-time could have had a major impact on the early universe, affecting matter distribution and galaxy formation. Strings of space-time could have acted as a gravitational force, causing Cosmic strings may have served as a framework for the material to collapse into the structures we see today. Some hypothesize that they may have played a role in the creation of gas galaxy clusters and even superclusters, the biggest structures in the cosmos. Moreover, cosmic strings could shed light on some anomalies in the cosmic microwave background radiation, which is a faint glow of radiation that remained after the Big Bang and gives us a picture of the universe at its. Despite the CMB's remarkable uniformity, there are tiny temperature fluctuations that correspond to areas of slightly higher or lower density. These fluctuations are believed to have been caused by cosmic strings, which could explain some of the observed anomalies in the temperature distribution and perhaps even the origins of galaxies. The universe is only 380,000 years old, might offer circumstantial evidence for the presence of cosmic strings. The hunt for these enigmatic objects has continued for decades, and although scientists have not found conclusive proof, they are still exploring various possibilities in the hopes of discovering them. One intriguing approach is to scan vast swaths of the sky for the unique lensing patterns that cosmic strings would create in the hopes of catching a glimpse of these elusive objects. Another strategy is to look for gravitational waves that cosmic strings are generating. As these observatories get smarter, they might be able to pick up on the subtle space-time ripples that cosmic string interactions cause. Another approach is to see if cosmic strings have any influence on the cosmic microwave background. Currently, scientists believe that quantum fluctuations in the early universe are responsible for the main fluctuations in the CMB, but cosmic strings could potentially leave secondary imprints that could be picked up with. With the use of high-precision measurements, researchers are searching for patterns in the cosmic microwave background, CMB, that could point to the existence of cosmic strings. The idea of traveling at the speed of light, FTL, has long captivated astronomers, science fiction authors, and anybody else who has ever gazed into the night sky and fantasized about the possibility of visiting faraway galaxies. However, the fundamental law of physics states that, as far as we know, no object can travel faster than light. Interstellar travel has hit a brick wall due to Einstein's theory of relativity. However, there is a theoretical concept called the allure drive that suggests a tantalizing alternative: warping space around an object instead of trying to move it faster than light. Miguel Allure, a physicist, proposed this idea, and it could allow spacecraft to travel to distant stars faster than light without violating the laws of. The theory of general relativity provides the theoretical basis for the allure drive, which describes how massive objects bend the fabric of space-time around them. Einstein demonstrated that gravity isn't simply a force that pulls objects together, but rather the result of space-time curving around massive objects like planets and stars. The theory suggests that if space-time can be bent and warped, then perhaps it could be manipulated to enable faster-than-light travel. The allure drive achieves this by generating a phenomenon called a warp bubble. In this hypothetical scenario, space-time is compressed in front of the spacecraft and expanded behind it, creating a pressure bubble. The spacecraft would then ride this wave of space-time, similar to how a surfer rides an ocean wave. It's important to note that the space surrounding the spacecraft would actually be moving faster than the speed of light, thereby avoiding the speed limit imposed by special relativity. In this scenario, the spacecraft and its occupants stay in a sort of bubble of normal space, free from the effects of relativistic phenomena like time dilation, which occurs when objects moving close to the speed of light experience time at a slower rate. Instead of light, space-time itself is moving, and this concept of warping space instead of and moving through it provides a clever workaround to the problem of fast transportation by spacecraft, FTS travel. While the idea of relativistic travel sounds intriguing, the practical challenges of developing an ALCU drive are enormous. One of the biggest is the requirement for exotic matter, which does not exist naturally in our universe, but is predicted to exist by quantum physics in order to create the warp bubble. This exotic matter would allow them to traverse vast distances at speeds faster than light. In his original paper, Alcubierre estimated that a stable warp drive would require exotic matter with a mass energy equal to the entire observable universe. However, recent studies have shown that this mass energy requirement could be reduced to that of a small planet, which is still far beyond our current technological capabilities. This is in contrast to the Casimir effect, which involves small amounts of negative energy. While developing a functional allure drive, we face several challenges. One of them is the stability of the warp bubble. Even if we could generate the negative energy needed to form the bubble, there's no guarantee that it would stay stable or that it could be controlled in a way that would allow for safe travel. Some theoretical models suggest that the bubble could collapse or behave unpredictably, which could pose a risk to our ability to travel, both the spacecraft and its surroundings. On top of that, some models suggest that a warp drive could build up harmful radiation levels while in use, which could be released in a disastrous burst when the spacecraft leaves the warp bubble. Despite all these problems, the theoretical framework of the Alub air drive is still a fascinating topic of study for physicists. It addresses some of the most fundamental questions in modern physics, like the nature of space-time energy and the fundamental. The concept of limits of travel ignites thought-provoking conversations regarding the possible outcomes of fast-traveling spacecraft, FTS, travel, especially in relation to the laws of nature and time itself. One of the most significant implications of FTS travel is the possibility that it would violate the principle of causality, which states that an event cannot occur before its cause. This rule appears to be a fundamental law of the universe, but in theory, FTL travel could disrupt this order. The time paradoxes that would ensue from arriving at a destination before it left would be a huge setback for any theory of fast-traveling spacecraft. On the other hand, in certain scenarios, FTL travel could open the door to closed Tim-like curves, which are paths through space-time that effectively allow for time travel. For instance, a spacecraft could go to a faraway star faster than light, turn around, and arrive at the star at a later date. Even in a theoretical setting, the laws of physics are based on the assumption that cause and effect follow a linear progression through time. If FTL travel were feasible, it could undermine this foundation, leading to a universe where time itself becomes a logical paradox. This is because it creates contradictions in the timeline and the possibility of changing past events, which are major reasons why many physicists are skeptical of it. Although the Allure drive is compatible with general relativity, it remains unclear how fast transportation through space, FTL, would interact with the laws of physics regarding time and causality. On the other hand, recent developments in quantum field theory have sparked a resurgence of interest in warp drive concepts, with the hope that new mathematical models can be developed to lower the energy requirements of such a drive. Although these models are still in the early stages of development, they imply that FTL travel may be possible, could be accomplished with more manageable amounts of exotic matter or other types of negative energy rather than the inconceivably high amounts of energy initially anticipated. If a warp drive were to ever be created, it would have far-reaching consequences for humanity. It would pave the way for the exploration of faraway galactic centers and star systems in a matter of days or weeks, instead of the thousands or millions of years required by current propulsion technologies. Space travel at the speed of light has the potential to transform our understanding of physics, providing new insights into the nature of space-time energy and the universe. It could also help us solve some of the biggest mysteries in modern physics, like the nature of dark matter and dark energy, or even allow us to visit planets orbiting distant stars, search for extraterrestrial life, or even colonize other worlds. A functional warp drive, ushered in by the merging of quantum mechanics and general relativity, would rank among humanity's crowning achievements, reshaping our perception of reality and the cosmos at large. However, according to quantum field theory, the vacuum isn't the bare space we usually picture it as, but rather a condition of the most fundamentally low energy for the quantum fields that encompass the entire cosmos. What if, instead, the universe isn't in its most fundamentally unstable state? One possible scenario is a false vacuum, in which the universe is in a metastable state that gives the impression of stability, but actually has a lower energy state. This means that the universe is currently in a shallow valley of energy, where it is stable, but could shift to a deeper, more stable valley, the true vacuum, through a process known as quantum tunneling, which could lead to disastrous and unpredictable outcomes. If the universe were to undergo a random transition from a false vacuum state to a true vacuum state, without any external trigger, in classical physics, it would have enormous consequences. The energy difference between the two states would explode in a huge burst, creating a bubble of true vacuum that would expand outward. And who knows, maybe it will never happen at all. The universe would be consumed by an expanding bubble traveling at the speed of light, destroying everything in its path. Particles with mass could lose it. Fundamental forces like electromagnetism could act differently, and the very structure of space-time could undergo changes. Stars, planets, and atoms wouldn't exist in this new vacuum state. The bubble would continue to expand, consuming everything in it. Unexpectedly, as light travels at the speed of sound, we would not be able to detect its approach. Instead, it would just arrive, destroying all matter and structure in its path. This unsettling notion of the universe spontaneously transitioning to a true vacuum is still purely theoretical. There is no proof that we are currently in a false vacuum, but the principles of quantum mechanics raise the possibility. Accordingly, the timing of such a transition is entirely uncertain. The discovery of the Higgs boson in 2012 has sparked new discussions about vacuum stability. The Higgs boson is connected to the Higgs field, which is crucial for particle mass, and its stability has been questioned in light of the current age of the universe. Whether vacuum decay is truly possible, it has not yet occurred, and the universe appears stable for the time being. Physicists study the properties of the Higgs boson and the masses of other particles, such as the top quark, to determine if the universe is stable or on the brink of instability. Based on what is currently known about the Higgs field, some physicists believe that the universe could be in a metastable vacuum, where the Higgs field is at a local minimum instead of the actual lowest energy state. To find out if this is the case, measurements have shown that the Higgs boson mass is a crucial factor. Although the cosmos may be stable for the time being, the unsettling prospect of what might happen on cosmic timescales remains. Quantum tunneling is a slow process on large scales, and the energy needed to trigger a vacuum decay event could be extremely high. Hence, even though the cosmos may be stable for the time being, the likelihood of a vacuum decay event occurring in the far future remains high. An event that could happen in our lifetime or in the next billion years is extremely unlikely, but it's also hard to say when it might happen, if it can happen at all. Since the universe has been around for more than 13 billion years without a transition like this, it's likely that conditions much beyond what we can see right now are necessary for false vacuum decay to occur. Ongoing research is trying to figure out if the universe is really metastable and whether. Theoretical models suggest that high-energy particle collisions, like those at the Large Hadron Collider, LHC, could reveal information about the early universe and the nature of quantum fields like the Higgs field. By crashing particles at extremely high energies, physicists aim to learn more about the characteristics of these fields and how they affect the vacuum stability. Cosmological observations of the universe's large-scale structure and the cosmic microwave background CMB radiation might also provide indirect evidence about the vacuum stability. While these collisions may not directly cause vacuum decay, they could reveal more about the underlying structure of the vacuum and whether the universe is in a stable or metastable state. The search for gravitational waves is one possible method to detect signs of vacuum instability. Another is to study the evolution of the early universe and the behavior of quantum fields during the Big Bang. This could lead scientists to evidence of previous phase transitions that could explain the vacuum state of the universe. One such source is the cosmic microwave background, CMB, which provides a snapshot of the universe 380,000 years after the Big Bang and may contain information about the behavior of quantum fields during that time. Though no such gravitational waves have been detected thus far, future detectors, such as the Laser Interferometer Space Antenna LISA, could aid in the hunt for the possibility that cosmic background radiation or the fabric of space-time bear imprints of vacuum decay or comparable phenomena that occurred early in the universe's history. This is all speculative, but it could be explained by gravitational waves, ripples in space-time caused by massive cosmic events. False vacuum decay. Investigating vacuum stability calls into question the ultimate destiny of the cosmos. If the cosmos is really metastable, then maybe it will turn into a true vacuum someday. This would have far-reaching effects, changing the rules of physics and wiping out our entire universe. But the enormous time scales involved make it highly unlikely that this will ever happen. Time loops in the warp of. As a solution to Einstein's general relativity equations, closed Tim-like curves, CTCs, symbolize paths in space-time that loop back on themselves, opening the possibility of time travel. On a closed Tim-like curve, an object or person could follow a trajectory through space and time that ultimately returns them to their starting point, both in terms of space and time. This implies that future events could. In Einstein's theory of general relativity, gravity is defined as the curvature of space-time caused by the presence of mass and energy. Large objects, such as stars and planets, bend space-time around them, influencing the motion of smaller objects. This curvature poses profound questions about the nature of time causality and the boundaries of our present understanding of the universe. Crossing both space and time, while the majority of solutions to Einstein's equations depict commonplace phenomena like planets in orbit around stars or the expansion of the universe, there are more exotic solutions that open the door to the possibility of closed time-like curves. These curves would lead an object to an earlier point in space-time, creating the possibility of a time loop. One of the most well-known and early examples of a space-time solution is Gödel's universe, proposed in 1949 by mathematician and physicist Kurt Gödel as a solution to Einstein's field equations, envisioned a universe in which space and time were bent in such a way that an object could travel in a closed loop, returning to its starting point in both realms. This intriguing example of how general relativity could enable time travel, despite the fact that our universe, in contrast to Gödel's hypothetical universe, which does not seem to match our own, the one we live in does not seem to resemble Gödel's rotating universe. However, the existence of closed Tim-like curves is not limited to this particular solution. In other theoretical models, especially those involving extremely curved or distorted regions of space-time, time loops become feasible and closed Tim-like curves can exist. Curves pose serious questions regarding the concept of causality, which is based on the idea that an event in the past can influence an event in the future. This notion appears to be a fundamental rule of the universe in our everyday lives. For example, when we drop a glass, it breaks because the impact of the fall causes the glass to shatter. However, in a universe with closed Tim-like curves, this order could be reversed, causing paradoxes and possible violations of causality. The famous grandfather paradox highlights this point. Imagine a scenario where a time traveler goes back in time and stops their own grandpa from meeting their grandma. If this were to happen, the time traveler would never have been born, which begs the question, how were they able to travel back in the first place? Paradoxes like this show how difficult CTCs are to explain, and the fact that they could violate causality is what makes them so controversial in theoretical physics. Some physicists think that nature must have a mechanism to stop these kinds of. It is worth noting that the equations of general relativity do not explicitly rule out the existence of CTCs, so the possibility remains that they could exist under certain very specific circumstances. Another intriguing possibility is the formation of wormholes, which are theoretical tunnels through space-time. These could theoretically link 2 points in space-time, enabling instantaneous travel between faraway places. There is an intriguing concept surrounding wormholes and their potential to create CTCs. However, there are concerns about causality violations and time paradoxes. Additionally, there's the possibility that time would pass more slowly at one end of the wormhole than the other due to time dilation. In this scenario, a person entering the wormhole could emerge at the other end at an earlier time, effectively creating a closed Tim-like curve and enabling time travel. Although wormholes with a negative energy density have not been found in nature, general relativity does allow for their creation and stabilization. Without this exotic matter, wormholes would collapse too quickly for anything to pass through, rendering them impractical for time travel. Despite the difficulties caused by CTCs, some physicists have speculated that quantum mechanics could provide a solution. Some researchers have proposed that quantum mechanics could enforce consistency in closed time-like curves by ensuring that any event in a time loop must be self-consistent. This would mean that paradoxical situations like the grandfather paradox would no longer be possible, as quantum uncertainty, which governs the behavior of particles at the smallest scales, governs the outcomes of events instead of dead determinism. If this were the case, quantum mechanics could limit what could happen in a closed time-like curve. For instance, if someone wanted to go back in time, they'd have to do it in a way that didn't cause a paradox. The events in the time loop would then self-correct, creating a consistent history where the relationships between causes and effects would still hold. This principle is sometimes called the Novikov self-consistency principle, and it states that any action, way back in time, could create a new alternate timeline separate from the original one. This would allow for the possibility of time travel without causing paradoxes, as events in the new timeline would not affect the original timeline line. While traveling through time, one must ensure that their actions are consistent with the history they experienced. Quantum mechanics also introduces the possibility of multiple timelines or parallel universes, which could offer another way to resolve the paradoxes associated with CTCs. Although not widely accepted, this idea does offer a potential solution to the problem of closed time-like curves in conjunction with the principles of quantum tunneling, which show how the laws of quantum mechanics differ from our traditional view of the world. In classical physics, for instance, an object is considered stuck if it lacks the energy to overcome a barrier. At the quantum level, however, particles aren't limited by such strict regulations. Instead, they exist in a probabilistic state, and in some cases they can tunnel through obstacles that classical physics would consider insurmountable. This phenomenon, known as quantum tunneling, contradicts our everyday experiences but is essential in many natural and technological processes. The fact that quantum particles are able to escape from classically bound boundaries is what drives some of the most fundamental reactions in the universe and suggests that quantum tunneling has fundamental implications for our understanding of the universe. Quantum mechanics describes particles as behaving like waves in the quantum world. A particle's position is not fixed until it is measured, but rather it has a probability distribution that spreads out over space. This probability wave can extend into regions where the particle would not be allowed classically, even if it lacks the energy to overcome a physical barrier. Transcend the barrier, implying a tiny but non-zero probability that the particle will emerge on the opposite side. This is the crux of quantum tunneling. One of the most crucial locations where quantum tunneling occurs is inside stars, like our Sun. Stars generate energy through nuclear fusion, a process wherein lighter atomic nuclei, like hydrogen, fuse to form heavier nuclei, like helium, releasing enormous quantities of energy in the process. Even though the nuclei inside stars don't have enough energy to overcome the electromagnetic repulsion in a classical sense, quantum tunneling provides a solution. This is because as all nuclei are positively charged and so repel each other due to the electromagnetic force. The stronger the repulsive force gets as the nuclei get closer together, making it seem impossible for fusion to occur at the temperatures and pressures present inside stars, at least according to classical physics. The ability to tunnel through barriers is essential for fusion to take place. Without quantum tunneling, stars like the Sun and stars in general would not be able to generate the energy that powers themselves and life. As we know, it would not be possible. Tunneling is also essential in superconductivity, a phenomenon that happens in some materials at extremely low temperatures. Temperatures where they can conduct electricity without resistance in ordinary materials. Electrons encounter resistance when they move through them, colliding with atoms and releasing heat as a result. In contrast, superconductors include a phenomenon known as quantum tunneling, in which two superconductors with a thin layer of material between them undergo zero-resistance movement without scattering, interfering layer between them. Despite the fact that classically electrons shouldn't be able to do so, quantum tunneling enables Kuppa pairs to tunnel through the barrier while maintaining the superconducting current. This phenomenon forms the basis of the Josephson effect, which is crucial for applications like sensitive magnetic field detectors, quantum computers, and superconducting quantum interference devices. Alpha decay is another important natural example of quantum tunneling. In alpha decay, a radioactive decay process, an atomic nucleus releases an alpha particle, a spherical particle with 2 proton and 2 neutron nuclei, into space. In a classical model, the alpha particle is unable to escape the nucleus due to the strong nuclear force, but it can do so via quantum tunneling, which happens naturally in some radioactive elements and is a possible explanation for. In addition to its use in stars, superconductors, and radioactive decay, quantum tunneling is also involved in theories regarding the fundamental structure of the universe. One such theory is inflationary cosmology, which postulates that the cosmos experienced a period of extremely fast expansion shortly after the Big Bang. This period of rapid expansion, known as inflation, helped to explain the uniformity of the universe on a large scale. On the other hand, not everywhere in space experienced the same rate of inflation, which could have resulted in a phenomenon called eternal inflation. In this case, pocket universes formed as a result of uneven inflation rates could have varied physical characteristics due to factors like quantum tunneling, which allows certain regions to travel from one vacuum state to another. In the multiverse hypothesis, which proposes that our universe is merely one among numerous with distinct physical laws and constants, quantum tunneling is seen as a crucial process by which new universes are born. This process involves regions of space tunneling to lower energy states, resulting in bubbles of space where inflation ceases and a new universe starts. Inflation is a crucial process that could result in different regions of space expanding at different rates, potentially giving rise to new pockets of space that could develop into separate universes. Quantum fluctuations, which happen on smaller scales but can reach cosmic sizes, play a crucial role in this process. Some of these universes could be similar to ours, while others could have completely different laws of physics. The cosmic microwave background radiation, which is the afterglow of the Big Bang, still carries the imprints of the Big Bang. These imprints, which shape the universe on a large scale, have an impact on the formation of galaxies, stars, and clusters of galaxies over billions of years. A combination of eternal inflation and quantum tunneling paints a picture of a universe that is endlessly expanding, forming new regions with distinct properties. This idea is related to string theory's landscape, which postulates that quantum tunneling not only powers the sun and enables superconductivity, but also allows regions of space to move between different points in the landscape, potentially creating new universes. In this picture, there are many possible vacuum states, each corresponding to a different set of physical laws. Our universe is just one point in this vast landscape. I hope you liked this video. If you did, please subscribe to my channel and leave a like. It explains radioactive decay and the strange but powerful nature of quantum mechanics, a field where particles can appear to defy classical logic by passing through barriers and changing our perception of reality.